Good morning, dear students. So in the last class, we were discussing about IPAC nomenclature, right? So did you understand everything? Yes. So did you practice? So did you go through the rules, then the different, how to name the different cationic complexes, anionic complexes, and when you have both cation and anion in the complex. So did you go through all the rules and how to name the compounds? Yes, okay, fine. So today we are going to start with the new next important topic. So the next important topic is isomerism. Okay. So this is also very important in coordination compounds. So important question is asked on coordination compounds. Okay. So let us see. So what is isomerism, students? Yes, what is isomerism? Yes, what is isomerism? You have studied isomerism in PU first year also. Yes, what do you mean by isomerism? So two or more compounds when they have same chemical formula but different arrangement. Is it? So when two or more compounds having same chemical formula but different arrangement of atoms, okay, and they differ. So because of the different arrangement of atoms, they differ in the physical as well as chemical properties. Okay, so they are called as isomers, and the phenomena is called as isomerism. And the phenomena is called as what? Isomerism. Is it clear? So what is isomers? So isomers, so when two or more compounds, when they are having same chemical formula. So the formula is same, only what differs is the way of arrangement. Okay, it differs in the arrangement of atoms. So because of the arrangement of atom, what becomes their physical as well as chemical properties are also changed. Okay, they differ from each other and they are called as what? Isomers, and the phenomena is called as what? Isomerism. And the phenomena is called as what? Isomerism. Okay, fine. So, so this is about isomerism. Now, this isomerism, it is divided or it is of two types. Okay, they are classified into two types. The first one is stereoisomerism. The first one is what? Stereoisomerism, and the second one is structural isomerism. Okay, stereoisomerism and structural isomerism. So first, let us start with structural isomerism. Okay. So let us start with structural isomerism. Now, what do you mean by structural isomerism? Okay, so the structural isomers, they are having same molecular formula. They are having what? Same molecular formula, but different structural arrangement. But different structural arrangement. Okay, so the arrangement of these atoms are different. Okay, so so that they are having different structural arrangement of ligands. Okay, around the central metal ion, around the central metal ion or metal atom. Okay, ion or atom. So So this is the structural isomerism. So please note down the definitions, very important. They will ask you any isomerism with example, or they can give you example and they will ask you identify the isomerism present in the above example. So like that. So you have to know, okay. So you need to know the definitions also, and you need to know different examples also, how to write the names. So what is structural isomerism? They are having same molecular formula but different structural arrangement of ligands around the central metal atom or ion. Okay, so they are called as structural isomerism. Now, this structural isomerism, these are further divided into four types. Okay, these are further divided into four types. First one is linkage isomerism. First one is linkage isomerism. Second one is what? Coordination isomerism. Okay, coordination isomerism. Next is ionization isomerism. Okay, ionization isomerism. Then the fourth one is solvate isomerism. Next one is what? Solvate isomerism. Okay, so these are the different types of structural isomerism. So remember what is isomerism? So what all we have seen? What is isomerism? So isomerism when two or more compounds having same molecular formula but different arrangement of atoms, okay, and because of which it differs in physical and chemical properties are called as isomers. Right, and the phenomena is called as isomerism. Right, then these isomerisms are further divided into two types. They are classified into two types: stereoisomerism and structural isomerism. What is structural isomerism? So they are having same molecular formula but different arrangement of ligands around the central metal atom or ion. So they are called as structural isomerism. So these are divided into four types: linkage, ionization, coordination, and solvate ionization. Okay. So let us see one now, and then we will go for stereoisomerism. Okay. So first we'll complete this complete structural isomerism. Okay. Let us complete first the structural isomerism, and then let us come to your stereoisomerism. Okay. So first, let us see linkage isomerism. Okay, linkage isomerism. So this is the first type. So what all things? Linkage, then was ionization. Next you have coordination, and fourth you have hydrate, or it is called as solvate ionization, isomerism. Okay. So first one is linkage isomerism. So what happens in linkage isomerism? So here it is having same molecular formula. Linkage isomerism, it is having same molecular formula, but it differs in the attachment of ligand. It differs in the linkage of the ligand. Suppose so here is an example. FeCl5NO2 3 minus. Okay. So you know that NO2 minus is what? It is a amphidentate ligand. Okay. It is a amphidentate ligand. Right. So this NO2, okay. So this NO2, it can link through this oxygen also, or else it can link through the nitrogen also. Right. You know this. Amphidentate ligand means what? When they have more than two, more than like when they have more than two this donor atoms in the same molecule, right? So this is NO2. So NO2 minus is what? It is amphidentate ligand. So here the mode of attachment. So there are two donor atom. One is nitrogen has lone pair of electrons. So this will donate. Another is your this oxygen atom. So at one time only one donor atom will get attached to the central metal atom. So here what is linkage? Linkage means how it will link. So the linkage means it differs only in the linking to the ligand. Okay. Sorry, linking, yes. Okay. So here So this is the example. So please note down the example for linkage isomerism. So complexes having same molecular formula but differ in the linkage of ligand or attachment of ligands to the central metal atom or ion are called as linkage isomerism. Are called as what? Linkage isomerism. Is it clear? Yes. So what happens in linkage isomerism? They are having same molecular formula, but the mode of attachment of the ligand to the central metal atom is different. So here you can see, if we see the example here, so let us see the example here. So if we are going through the example here, you can see the nitrogen atom has link. Okay, here the nitrogen atom has link, and here your oxygen atom has linked. Okay, here your what? Oxygen atom has linked. No, this only correct. Okay, so your nitrogen atom has link and here your oxygen atom has link. So the mode of attachment is different to the ligand, okay, to the central metal atom. Okay, fine. So this is clear. So I'll give you some more examples. So please note down this, very important. Okay, they will ask you, what is linkage isomerism? Give examples. So 2 marks question. 1 mark for the definition, 1 mark for the example. So you need to know the example. So please note it down. So second example, what I'm giving you, cobalt NH3 NO2 Cl2 and cobalt NH3 ONO Cl2. Okay. So here, what is happening? So cobalt is there. Okay. So your NH3s. Okay, and here what is happening? Your nitrogen is linked to one is through the nitrogen itself. Okay, and another is, so let me write it here. Cobalt in the center, NH3, 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 and here is oxygen N. Okay, so like this. So this is the mode of attachment. So another example of the, so please note it down. So example number 2. Okay, example number 2. Take take one more chromium Cr H2O5 and SCN. Okay. So in this case, what you can see that amphidentate ligands. Okay, whenever you have amphidentate ligands, so these amphidentate ligands will show linkage isomerism. Okay. So we know that thiocyanate is also an amphidentate ligand. So it can link from S also. Okay, and it can link to nitrogen also, right? So this is about your amphidentate. This is about your linkage isomer. Okay, so this is the third example. Did you note down the question? So here, what is happening? Here it is bonding to sulfur and here it is bonding to nitrogen. Is it clear? Is it clear up to here? Yes, okay, fine. So let us go for the next one. Next is coordination isomerism. Next is coordination isomerism. So it occurs in coordination compounds. Okay, so coordination isomerism, it occurs in coordination compounds containing complex cations and complex anions. Okay, so this is occurring in the complex having complex cations also. Okay, and complex anions also. So it appears in the complex compounds. Okay, it appears in the complex compounds having cations and complex and ions. Fine. Okay, so it arises due to the interchange of ligands. Why it arises? It arises due to interchange of ligands between this complex cations and complex anions. Okay, uh, of different metal ions. So let us see the example. So here you can see first example. Okay, zinc NH34 and CuCl4. Here you can see that what is happening here. So this is your cation complex. This is your anion complex. So what is happening here? There is a interchange of this central metal, that is interchange of the ligands with the central metal atom. So here zinc is there, here copper is there, here copper is there, here zinc is there. So it occurs in the coordination complex or complex compounds with complex cation and complex anions. Okay, with the interchange of ligands of different metal ions, that is between the coordination sphere. Okay, so please note down the example, note down the example. So here, so this is the example. So interchange of ligands takes place in the complex compounds. Is it clear? Next one is ionization isomerism. Next one is our ionization isomerism. So complexes having same molecular formula, okay, the same molecular formula, but it dissolved in solvent produces different ion. Okay, but when it dissolves, okay, when the complex is dissolved, the solvent, okay, in solvent, it produces different ion. What happens? It produces what? Different ions. Okay. So complexes, they are having same molecular formula, but what happens? But when you dissolve it in solvent, okay, they will produce different ions. Okay, and thus they are called as ionization isomers, and the phenomena is called as ionization isomerism. So note down the examples. Okay, so here cobalt NH3 5 SO4, okay, Br. So when this you add it in solvent, so this may dissociate into cobalt NH3 Br SO4 also. Okay, so the when you add it in solvent, okay, what happens? The solvent, the ions may change. Okay, the it may dissolve. Okay, and they produce different ions when you add it in water. Okay, so please note down this. Please note down this. Yes. So, did you write down? Okay. So here, see here. So what all things we have discussed today? So we have discussed isomerism. Okay, we have discussed isomerism. What is isomerism? Then we have discussed the two types of isomerism. The first was the structural isomerism, and the second was stereoisomerism. Then in structural isomerism, okay. So again, we have discussed what the first one was linkage isomerism. Okay, first we have seen linkage isomerism, then we have seen coordination isomerism, and now what we saw was ionization isomerism. So ionization isomerism is what? The complex will have same molecular formula, but when you dissolve it in solvent, okay, it will produce different ions. Okay, so please note down the example. So your so when you add your cobalt NH35 sulfate Br, okay, so what will happen when you add it in? So this is red violet color. Okay, so when Br is outside the sphere, so it will be red violet color, and when you dissolve it in solvent, okay, so it may also dissociate as Br will be inside the sphere, and the sulfate will be outside the sphere. So it may vary. So because of the change in the ions, okay, position of the ions here. Okay, so when you add it in solvent, what is happening? The different ions are produced. So because of that, the complex color is also different. So here you can see it is red violet, and here it is red. Okay, so here this will dissociate to this way. So please note it down. Okay. So this was about ionization. Then last one we'll see hydrate. Okay. Last one is hydrate isomerism or solvate isomerism. So another name, solvate isomerism. Same molecular formula but differ in water molecule. Okay. Same molecular formula but differ what? But they differ in water molecule inside and outside. Got it? So they are having same chemical formula, okay, molecular formula. But what happens? The number of water molecule associated inside and outside will vary. Okay. For example, for example, chromium H2O 6 Cl3. Okay. So this is what? So chromium is there and 6 water molecules are associated with this. And this particular complex is violet in color. Okay, this is violet in color. Then if we say another, so chromium H2O5 Cl, okay, Cl2 dot H2O. So this is gray in color. This is what? Gray green in color. Okay, this is gray green in color. So here what is happening? One of the water molecule is replaced by the Cl, and that water molecule is outside the sphere. Okay, so here three Cls were there. So one of the Cl has come inside the sphere. Last one, chromium H2O4 and Cl2 Cl dot 2H2O. So this is green in color. This is green in color. So here in this three, okay, you can see the molecular formula is same, but the number of water molecule associated inside and outside the sphere is different. So this is about hydrate isomerism or solvate isomerism. Is it clear? So please go through the examples, very important. So any doubts up to yours? So we have seen isomerism and structural isomerism. In structural isomerism, we have discussed four types of isomerism. That is your ionization isomerism, linkage isomerism, and coordination isomerism and hydrate isomerism. Okay, is it clear? Okay, so this completes our structural isomerism. Next, we are going to discuss is the stereoisomerism. Next is what? Stereoisomerism. So what is stereoisomerism? Same, okay, stereoisomers, they are having same chemical formula. So the chemical formula is the same and chemical bonds, but they have different spatial arrangement. Okay, so they are having same chemical formula and chemical bonds, but what happens? Okay, different but different spatial arrangement. Spatial arrangement. What do you mean by spatial arrangement? In space. The arrangement of atoms in space is different. So what is stereoisomerism? They are having same chemical formula and the chemical bonds are same, but they differ in the spatial arrangement. Where it differs in the spatial arrangement. Okay, so in this there are two types, geometrical isomerism and optical isomerism. Very important, very important. Okay, so these are also important, but these are very important. Okay, so please, you should know all these six types of isomerism. You should know all the six types of isomerism. In structural, you should know all the four, and in your stereoisomerism, you should know these two, geometrical and optical. So first, let us see what is geometrical isomerism. Okay. So what is geometrical isomerism? So the isomerism, geometrical isomerism, it arises due to the Okay, so geometrical isomerism, it arises due to different possible of geometrical arrangement of ligands. So how the ligands get arranged in different manners. So because of this, the geometrical isomerism come into picture. So suppose we have a type of arrangement where you have metal. Okay, metal we represented as M, and we have two types of ligand. One is A and another is B. So A, number of ligands of A is 2 and number of ligands of B is 2. So the arrangement of the ligands around the central metal atom, so it depends on that. So here, if the arrangement of the ligand, so there are two types of ligand. What did I discuss? So there are two types of ligand. One is A, one is B. Here the number of atoms of ligand A is 2, and here there are 2. So if if the ligand A has is on one side and ligand B is on another side, so this type of arrangement is called as a cis arrangement. Okay. So here the coordination number of the complex is what? Yes, what is the coordination number? Coordination number means how many number of ligands are present around the central metal ion. Can anyone tell me what is the coordination number here? What is the coordination number? What is coordination number? Coordination number is the number of ligands around the central metal atom or ion. So how many ligands are present? Nobody knows? Yes? So it is 4, right? Because the number of ligands are 2 plus 2, 4. So this is a central metal atom. So we are having 4 ligands. Now here, one type of ligand is on one side, another type of ligand is on other side. So this type of arrangement is called as a cis arrangement. Now, in another case, okay, there is one more case where the one type of ligand is on opposite side and another type of ligand is again on opposite side. So this type of arrangement is called as a trans arrangement. What they are called as trans arrangement. Okay. So what type of ligands? So when you have same type of ligands in the complex, then they're called as what? If you have same types of ligand in the complex, then they're called as homoleptic complexes, right? We have studied this. So when you have same type of ligands, okay, in the complex, then they are called as homoleptic complexes. And when they have different type of ligands, they are called as what? Heteroleptic. Right, this we have discussed. So when we have same type of ligands, homoleptic. When we have different type of ligand, then it is heteroleptic. Okay. So if the ligands are on adjacent side, what do you mean by adjacent side? Opposite side. So when the ligands are on the opposite side, okay, then what? Then they give rise to what? They give rise to when they are on opposite side, sorry, when they are on opposite side, then they give rise to trans arrangement. Okay, when they are opposite, then they give rise to trans. When they are on adjacent side, adjacent means on the same side. Okay, adjacent means on the same side, then it gives rise to cis. So in the heteroleptic, ligands, so this type of arrangement is possible. Okay, so when the ligands are on the opposite side, trans arrangement. When they are on the adjacent side, cis arrangement. So geometrical isomerism in the compounds, complex compounds with coordination number 4. Coordination number 4, why? Because the arrangement of ligands around the central metal atom, the number of ligand presents are 4. Okay, so it will give rise to 2. So this is one example. So copy down the example, that is PT, NH3 twice and Cl2. So PT in the center. So if we have ammonia at the adjacent side, that is on the same side, then this gives rise to what? This gives rise to cis. Then PT in the center and Cl here, NH3 here, NH3 here, then this gives rise to trans. Okay, is it clear about geometrical isomerism? Very important, very important. Yes, geometrical isomerism with coordination number 4. Is it clear? So this is with this type of arrangement when you have a square planar complex. Okay, when you have a square planar complex. Okay. So in this arrangement, square planar complex, so these are the two possibilities. One is a cis, and another is the trans. Okay. Now suppose, okay, now suppose if I have M, A, B, C, D. So I have 4 different ligands. Okay. So square planar complex which with A, B, C, D ligands. Okay. That is 4 different ligands. So in that time it will show 2 cis isomers and they will show 2 uh, one trans isomerism. So how it is possible? So metal in the center. So let us arrange. So A, this will be B. Sorry, A, and I'll write it as B in the opposite side. B. Then this is C and this is D. So this is one arrangement. Then the second arrangement, A, M in the center. Then A, B, then C and D. Okay. Then another arrangement, metal in the center, A, then B, then this is C, and this is D. Another arrangement, metal in the center, then A, then here B, C, and D. So here two cis, okay, two cis and two. So this is only, so here you can see that the A, C, B, D. So this is same type. Okay, here you can see it is same type. So A, then your B, they are on the same side. So AB is on the same side. CD is also on the same side. So CD also is on the same side. So this is only one. So this is third one. So one trans. Okay, so there are how many? Two cis and two trans. So here you can see this is on the same side, but here it is on the opposite side, right? So we have given two different arrangements. So here these two are on the same side. So this is a cis. So so whenever you have a complex of the type M, A, B, C, D, that is trans is possible. Okay, is it clear? Symbolism. Okay. And first one we have seen with the coordination number Ma2B2 complex. So geometrical isomerism in complexes with coordination number 4. What is coordination number? The number of ligands around the central metal atom or ion is called as a coordination number. So in the what is homoleptic ligands? Homoleptic ligands means when you have same type of ligands. Okay. In the homoleptic complexes means what? When you have same type of ligand present in the complex. Heteroleptic means when you have different type of ligand present in the complex, then they are called as. So in heteroleptic complexes, what happens if the ligands are on the adjacent side, then they give rise to cis arrangement. If the ligands are on the opposite side, then they give rise to trans arrangement. So this much you need to know. So the remaining part, so next we are going to see the geometrical isomerism in complex with coordination number 6. What do you mean by coordination number 6? Metal is there, okay, and two types of ligands are there. Okay, so here the number of ligands are how many? 6. So if the coordination, if the number of ligands around the central metal atom are 6, okay, so this is the coordination number 6. Okay, so the number of ligands around the central metal atom are 6. So this gives rise to coordination number 6. Okay, so this particular coordination that is geometrical isomers in coordinate in complexes with coordination number 6. Okay, so let us discuss this in the next class. Is it clear up to here? Okay, so you should not get confused. So I'm not discussing this because again it will be more confusion. So these all things. What is isomerism? What is structural isomerism? What is stereoisomerism? Then in type of structural isomerism, we have discussed what is ionization isomerism, solvate isomerism, coordination isomerism, and one more was ionization isomerism. Okay. Then in stereoisomerism, we have discussed about geometrical isomerism. So the remaining part of geometrical isomerism and optical isomerism. So let us discuss in the next class. Is it clear up to here? Yes. Any doubts? So please go through the things, whatever I have been told. Okay, if you go through the things, then only it will be clear. Fine. Okay. So any doubts up to here? Yes, students. Any doubts? Okay, fine. So I shall end the session here. Okay. So the remaining things we shall discuss in the next class. Thank you.